In this lecture, I will give you some examples of ADCME usage and to help you get familiarized with ADCME software. I will talk about the philosophy behind this software as I show you some code snippets. So let's get started. So first, let's open Junior instance and using ADCME. Yeah, as we saw in lectures, we want to create a computational graph. For creating a computational graph, we always want some the blue boxes in the computational graph. That's the starting point for the data, and that is serves as the edges without input node. So to create those blue boxes, we have two ways to do that. The first one is to use constant. And the constant means that A will not get updated in the optimization procedure because eventually we want to use ADCME to do inverse modeling, and eventually we want to use gradient-based optimization. So something must be updated and something must remain the same, like the data, or for example, the boundary conditions may remain the same for all the simulation. So the constant is a function which takes in a junior array or junior number. For example, let's consider ones. Let's create a vector of ones for A. Okay, then this command will create an edge in the computational graph. So and the edge values is ones 10. Now let's create a variable. This is the second important function in ADCME, where you must differentiate between constant and variable. By variable, what I meant here is that this B may be updated during the course of the optimization, and actually this is the optimizable function, optimizable parameter, which you seek to optimize that. And variable is also a function. It takes initial value of a B. Let's create an initial value using random 10. So you already have two edges. Now let's create some operators to get a computational graph. Let's formulate the loss function that compare the discrepancy between A and B using L2 loss. The first step is to compute the discrepancy. Let's compute A, B diff, which is just A, B minus A. And this minus operator is just a node in the computational graph. It takes B and A as input and output another tensor, which is AB diff. So AB diff depends on A and B. Whenever B changes, AB diff will also change. AB diff is a vector of 10. We want to square each component of AB diff. So AB diff square is equal to AB diff squared, and because of the operator overloading, this is this square operator is the same as that in the junior library. So this is a square sum. Is the square of each component of AB diff. So finally, we want to create a loss function by summing it up. So we get a scalar loss function, and sum is also an operator which takes a tensor and outputs another tensor. The input is AB diff square and the output is loss function. We can say we did not explicitly construct the computational graph, but as we code the dependencies between different tensors, we are actually implicitly constructing the computation graph. The backend of ADCME, that is TensorFlow, already records all the dependencies and construct a computational graph underlying this program. So let's do some. Let's first inspect the values of A and B. To do that, we need to create a session and initialize the session. And when you create a session, that means you create a driver for executing this computational graph. And when you do the init size, it will populate the values into this variable. So the next time you initialize, the variables might be different. Okay, so we already have this sys. So let's inspect some values. Inspect A. You can just run sys A. And inspect B. And you have this value. Okay, let's say what's the last function. You have this. Okay, the next step is that we want to minimize the difference between A and B. We already know that the optimal value for B is 1:10. Let's say if we can get that. To do that, we can of course extract the gradients. To extract the gradients of a loss function with respect to B, you can just tap gradients, loss B, and this is grad B, and this is a ladder tensor which is of length 10, and you can use this gradient. You can run out this gradient, and it will give you the gradient value. You can use this gradient to craft your own solvers, but now we are going to use BFGS solver. This is a built-in solver. In ADCME, you also have other solvers like IPOpt or NLOpt or any other kinds of solvers that is commonly used in scientific computing. And we just minimize this loss. Okay, you can see after 2 iterations it converges. This is actually obvious because you have a quadratic function, and for optimizers, the quasi-Newton optimizers, it usually converges within several steps. So let's say our B, if it is the correct value, you can see that we recover once always. So this is how you think about the computational graph and the edges and the nodes whenever you write this program. And all the operators are similar to the Julian syntax, so you do not have to worry about remember new rules and remember different APIs. Yeah, that's basically the workflow for using ADCME.